Now, we will take up one more problem, the problem number 44. A compound bar consisting of bronze, aluminium, and steel segments is loaded axially as shown in this figure. Determine the maximum allowable value of P if the change in length of bar is not to exceed 2 mm and the working stresses in each material of the bar is indicated in the table below is not to be exceeded. So the material which is bronze, aluminium and steel, for area which is measured in mm square, the bronze will have 450 mm square, aluminium will going to have 600 mm square, and the steel will have 300 mm square. And then it comes to the elastic modulus, which is measured in MPa, bronze as 0.83 into 10 to the power of 5, aluminium as 0.7 into 10 to the power of 5, and the steel will be 2 into 10 to the power of 5. Similarly, the working stress sigma W will be equal to, which is measured in MPa, where bronze is 120, aluminium is 80 MPa, and the steel will be 140 MPa. Now, first we are going to consider the equilibrium of the bar. So, when you are considering the equilibrium of the bar, so here, load acting towards the right side will be equal to the load acting towards the left side. So, the load acting towards the right side is 3P plus 2P, and the load acting towards the left side will be P plus 4P, which is equal to 5P. So, therefore, 5P is equal to 5P, hence it is the bar in equilibrium condition. Now, we will going to consider the equilibrium of the bar individually. When you are considering the bronze bar, on the left end we have 3P which is acting towards the right side, so it is compressive here. Now, when you are considering to the right end of the bronze bar, you have P which is acting towards the left, and 4P which is acting towards the left, and 2P which is acting towards the right. When you are considering that, so the bronze bar will going to have minus P minus 4P, which becomes minus 5P, plus 2P, which is equal to minus 3P. So the bronze bar will be in compressive in nature, wherein 3P is in the left direction and 3P is on the again on the right end. It will be 3P on the left right side and on the left end, and minus 3P, that is toward the left side on the right end. So the bronze bar will be in compressive in nature. When you are considering for the aluminium bar, we have 3P towards the left, right, and P towards the left. So 3P minus 3P plus P will be equal to minus 2P. Again, it will going to be acting in the right direction. And in the left end, and the right end, you have minus 4P plus 2P, which is equal to again minus 2P. So again, aluminium bar will also be in compression, having 2P as the workload or the force. When you are considering the steel bar, 2P towards the left side, towards the right side on the right hand, which is tensile. On the forces which is acting on the left hand side will be minus 3P plus P plus 4P, that is 5P minus 3P, which will be equal to 2P, which will going to be acting again to the left side. So it will be tensile in nature. Therefore, the bronze bar will be compressive, the aluminium bar will be compressive, but whereas steel bar will be in tensile. Now, the contraction of the bronze segment delta LB will be equal to, what is that? PB into LB by AB into EB. You know that PB is 3P into length of the bronze bar is 600 divided by area of bronze bar is just 450 into 0.83 into 10 to the power of 5. On substitution and simplification, you will going to get it as 4.8193 into 10 to the power of minus 5P. Similarly, the contraction of aluminium segment delta L will be equal to, it is 2P. So that will be PAL into LAL by AAL into EAL. So PAL is nothing but 2P into length of the segment is 1000 divided by area of the aluminium segment, which will be 600 into 0.7 into 10 to the power of 5, which is the Young's modulus of aluminium. So on simplification, again you are going to get it as 4.67619 into 10 to the power of minus 5P. Similarly, when you are considering the contraction of the elongation of the steel segment, delta L S will be equal to PS into LS by AS into ES, which will be equal to 2P into 800 by 300 into 2 into 10 to the power of 5. So on simplification, you will going to get it as 2.667 into 10 to the power of minus 5P. So what is the net deformation in the bar? The net deformation in the bar, delta L, will be equal to delta LB plus delta LAL plus delta LAS. So that is, the net deformation should not increase 2 mm. So therefore it is 2 is equal to minus 4.8193 into P into 10 to the power of minus 5 minus 4.7619 into 10 to the power of minus 5 into P plus 2.667 into 10 to the power of minus 5P. Therefore, taking the 10 to the power of minus 5P as a common factor into minus 4.8193 minus 4.7619 into 2 plus 4.7619 plus 2.667. So on simplification, you are going to get it as 10 to the power of minus 5P into 6.9142. Therefore, which is on the contraction. Therefore, P will be equal to 28925 Newton. So that will be equal to 28.925 kilonewton. Allowable value of P for 2 mm deformation, which will be 28.2925 kilonewton. Also, the working stress in the bronze bar sigma BW will be equal to PB by AB. So we have 120 will be equal to PB is nothing but 3P by AB is 450. So 3P is equal to 120 into 450. Therefore, P will be equal to 18,000 Newton, which will be equal to 18 kilonewton. That is, the maximum allowable stress value of P in bronze bar will be equal to 18 kilonewton. So this is all. And the working stress in the aluminium bar sigma ALW will be PAL by AAL. So you know the working stress AT will be equal to 2P into 2P by 600. So P will be equal to 24,000 Newton, which is equal to 24 kilonewton. Therefore, that is, the maximum allowable value of P in aluminium bar is 24 kilonewton. So working stress in the steel bar sigma SW will be equal to PS into PS by AS, which is working stress is 140 will be equal to 2P by 300. So that will be equal to P, capital P will be equal to 21,000 Newton, which is equal to 21 kilonewton. That is, maximum allowable value of capital P in steel bar will be equal to 21 kilonewton. Now we are going to take up one more problem. Determine the stresses in various segments of the circular bar, which is shown in the figure. So number 1, compute the total elongation assuming Young's modulus of steel to be 195 GPa. So problem number 2. In the subheading, determine the length of the middle segment so that the bar length does not change under the applied load. So as we have the circular bar which is shown in this figure, D1 is to 20 mm between A and B, and D2 will be equal to 25 mm between B and C, and D3 will be equal to 15 between C and D. And then the length of the AB is 100 and BC is 200 and CD is 150. So the one end of the bar is fixed here, and the load is applied at the other end, which is 100 kilonewton. Then at the junction of 1 and 2 you have 300. At the junction of 2 and 3 you have 250 kilonewton. And finally you are going to have P4, which is acting toward the right side. Now first we are going to consider the equilibrium of the bar. So the equilibrium of the bar will be equal to the load acting towards the right side should be equal to the load acting towards the left side. What is the load which is acting towards the right side, which is P4 plus 300, which will be equal to 100 plus 250. Therefore, the value of P4 will be equal to 50 kilonewton. So what is the free body diagram says? The free body diagram says, which is when you are considering for the segment AB, which is 300 on the plus side, 250 on the minus side, and 50 on the plus side. So the load acting towards the right side, which is tensile, is positive on the right end, and the load acting towards the left side and the right end will be minus. So 300 plus 50 minus 250, which will be equal to 100 kilonewton. On the left hand side, it is already, which is 100 kilonewton. Therefore, AB in equilibrium condition having diameter of 20 mm and the length will be equal to 100 mm. And you have a tensile load of 100 kilonewton. Now, when you are considering between B and C, the B will have on the left end, we are going to have 100 kilonewton toward the left side and 300 kilonewton toward the right side. So 100 minus 300 will be equal to minus 200. So the load will be acting toward the right side on the left end. And similarly, on the right end, we are going to have 250 acting toward the left and 50 is acting towards the right. So then it will be minus 250 plus 50, which will be equal to minus 200 kilonewton. So since on the left hand side is also minus 200, on the right hand side is also minus 200, therefore the segment BC will be in compressive in nature, or the compressive load. And the diameter of the segment there is 25 and the length of the segment is 200. Now when you are considering the third one, that is between C and D, on the left hand side, you will going to have three loads are acting, which is three forces which is acting. One is 100 minus 300 minus 100 minus 300 plus 250 minus 100 plus 300 plus 250, which is equal to 50 kilonewton on the left hand side. Similarly, on the right hand side, to the right side, you are going to have 50 kilonewton, so both will going to be under the tensile. To summarize, the segment AB will going to have a tensile force, and the segment 2, that is BC, will going to have the compressive, which is 200 kilonewton, and segment CD will going to have a tensile again, which is 50 kilonewton. So what are the stresses in the various segments? So stress in the segment 1, sigma 1 will be equal to P1 by A1. So P1 we know 100 kilonewton, 100 into 10 to the power of 3 divided by pi by 4 into 20 square. So on simplification, you will going to get it as 318.31 Newton per mm square, which is tensile. Similarly, stress in the segment 2, which is sigma 2, is equal to P2 by A2, which is equal to 200 into 10 to the power of 3 by pi by 4 into 25 square, which is equal to 407.44 Newton per mm square. Again, it is in compressive nature. Stress in the segment 3, sigma 3 will be equal to P3 by A3, which is equal to 50 into 10 to the power of 3 by pi by 4 into 15 square. Again, 282.94 Newton per mm square, which will be in tensile. So what is the total elongation of the bar? The total elongation of the bar, considering E is equal to 195 into 10 to the power of 3 Newton per mm square. So elongation of the segment 1, which is delta L1, because the load applied is tensile, P1 into L1 by A1 into E. So what is P1? P1 by A1 is sigma 1 into L1 by E. So what is sigma 1? Which is 318.31 into 100 divided by Young's modulus of steel. Young's modulus of the segment is 195 into 10 to the power of 3. On simplification, you will going to get it as 0.163 mm. So then, as the second segment is compressive in nature, so contraction of segment 2 will be equal to delta L2, which is P2 into L2 by E2 into E, which is equal to sigma 2 into L2 by E, which is equal to sigma 2 is 407.44 into 200 divided by 195 into 10 to the power of 3. On simplification, it is 0.418 mm, but it is compressive stress, so compressive in nature. So elongation of the segment 3, which is delta L3, will be equal to P3 into L3 by A3 into E. That is nothing but sigma 3 into L3 by E, which is equal to, substitute the value of sigma 3 as 282.94, and the length of the segment is 150 divided by Young's modulus is 195 into 10 to the power of 3. So on simplification, you will going to get it as 0.218. Therefore, the total elongation of the bar delta L will be equal to delta L1 plus delta L2 plus delta L3. On simplification, you substitute the value of delta L1, which is 0.163, minus, because the second one is in contraction, so which is equal to 0.418 plus 0.218. So on simplification, you will going to get it as minus 0.037 mm. So total deformation of the bar delta L will be equal to 0.037. Since it is a negative sign, it is contraction in HR. So length of the middle segment for zero elongation of the bar. If you are considering the length of the middle segment, total deformation of bar delta L will be equal to delta L1 plus delta L2 plus delta L3, that is equal to 0, which is equal to P1 into L1 by A1 into E minus P2 into L2 by A2 into E plus P3 into L3 by A3 into E. So that is 0 equals. So when you are calculating, you are getting all the values, that is 0.163 minus contraction in the segment BC will be equal to minus sigma 2 into L2 by E plus 0.218. So that means minus 0. Sigma 2 into L2 by E. So we want to find out the length of the middle segment. So on simplification, 407.44 into L2 by 195 into 10 to the power of 3, which is equal to, add up these two, 0.3814, then 0.3812. Therefore, L2, that is length of the middle segment, will be equal to 182.346 mm. So for the zero deformation of the bar. So this is how you will be able to solve this particular problem. Thank you.